Good evening and welcome to the live sessions for the course on Computational Science and Engineering. This course is taught by Professor Ashok Dey, who is a member of the faculty of Department of Aerospace Engineering at IIT Kanpur. And I am Sourav Goswami. I am a PhD candidate in the Department of Mechanical Engineering at IIT Bombay, and I'll be the teaching assistant for this course. Now, in the general conduct of this course, we every week we'll be recapitulating the key concepts and course content covered during the week. And after revising these concepts, we will try to solve a few exemplary problems, which will help reinforce our concepts, test them, and also help us solve the assignment problems that are due each week. And for seamless communication, I'll request that rather than unmuting and starting to talk, you raise your hand or type your question in the chat box, and from time to time, I'll be checking it, and we can discuss and go over questions. And once we're done, I request that you mute again. So before we start going over the contents for this week, I would like to just talk in general about the need and the motivation for this course. So as we know that our understanding of the universe is based on observations of the physical phenomena around us, and when we are trying to test a hypothesis in the lab, this takes on the form of experimentation, whereas wherein we have a system, we subject the system to certain external forces or stimuli, and we record its response, and we try to come up with a relationship between the input stimuli and the output response, and this is how we model the behavior of the system. Now, this is the most exact and the most accurate way to go about it, and within experimental bounds and within, say, measurement tolerances and measurement errors, this is the uh, sacred truth. And whatever you observe during experimentation, that is exactly how the phenomenon is happening. Now, another way to uh, study or describe phenomena is the analytical method, where you try to come up with an analytical relationship which describes the inputs and outputs of a system and quantify its behavior. Of course, such analytical models again uh, try to only model the most important physics, or say the most dominant physics, and there might be some aspects which are ignored and neglected, of course, under reasonable assumptions. And we see that even with those assumptions, the predicted behavior of the system is in good agreement with what is experimentally observed. This is the analytical description of a system. The third, and perhaps in recent times the most important, is the computational description, or the computational method and computational, say, modeling of a system, wherein, uh, say, even if we are able to obtain some analytical relationship, so a priori, it's not at all clear that we can have some relationship. We can have observations that appear random, and there is no simple mathematical relationship which can be used to link the inputs to the outputs on a consistent basis. It might very well be that our observations and are totally cannot be correlated, or we cannot, say, fit a mathematical relationship to our data. In the event that such a mathematical description is possible and you have what is called an analytical model, which can be, say, a single governing equation, or it can be a system of governing equations, or for each physics, say, you can have sets of equations. Depending on what physics you are including, your number of equations will vary. Even in such cases, even when you have a complete description of the system in terms of the governing equations, typically which are in physics, they might be partial differential equations. Often for describing, say, control systems, it can be ordinary differential equations as well. Even in such cases where you have or you are able to obtain the governing equation, you need not always be able to solve it because, as we are aware, do exist equations for which closed form solutions may not be readily available, or even if they are, they may only be available under uh, a certain specific set of boundary conditions. Now, how do you go about it then? That is where these computational methods come in. That is, even in situations where you do not have a closed form analytical solution, you may still be able to obtain a numerical solution. Of course, subject to certain error. Another key aspect is, say, even if you are able to solve for your equations, the number of equations itself is so large that manually it becomes almost untractable. Even with powerful computers, if you try to solve for the full system, it may not be computationally say feasible or practical, because even if you know that you can brute force your way through it and solve all of the equations, it might take an unreasonably long amount of time or an unreasonably large amount of computational resources to arrive at the solution. Whereas for most engineering cases, being engineers, we all we want is a good solution or a solution that is close enough. Of course, precision matters, but even if your solution is not exact, but it's good enough within some error bounds, more often than not, it will do the job. And in such cases, computational methods can help us scale down your problem domain. It can help, say, reduce the dimensions of the problem and can help you obtain a solution or predict the behavior of systems. Now, another way in which computational methods are very important is the mostly the limitation of experimental observations. So I am from a mechanical engineering background and I work primarily in additive manufacturing. I would like to give you the example of additive manufacturing itself, wherein you are depositing wire or powder on a plate. So it's like 3D printing itself, just with metal. And in this case, you might have an energy source such as a laser, which is helping to melt the powder and wire. It is getting deposited. Some geometry, such as a simple cube, is getting built. And physically, we can see this. Perhaps even if you fit some sensors into your 3D printing machine, you may even be able to extract some of these variables or information, such as, say, the temperature at the moving tip of the energy source. Even then, there are other things such as the temperature within the system, the cooling rate or the rate at which this temperature is decreasing. Since we are only able to see the surface and metal is opaque to say visible light, we don't really know what is happening inside. There is a molten pool of liquid metal. What are the velocities in that pool? What is the direction of flow? And there are similarly many different physically important parameters which are nigh impossible to obtain experimentally, just because there is a limitation in the way with which we can measure them. However, once you have, say, a model of a system which is faithful, and you have validated your model and calibrated it to your system, you can expect that even the information that you get from the system, say you for your additive manufacturing model, you measured the temperature on the top of the plate, and your model also is giving you a temperature profile. They are reasonably good, so they match. Your model is validated. Based on this, you can reasonably assume that all other predictions that your model will give, such as, for instance, the fluid flow velocities or the length and depth of the melt pool, should also be reasonably accurate. Of course, I am just simplifying matters a lot. There is a lot of that goes inside modeling such a multi-physics problem. But this is the general idea. So we see that computational methods are very important. And if the audience of this course, I expect you to be from an engineering background, whether it be from the bachelor's, master's, or doctoral level. You would have done at least one course on numerical methods during your time, and you would have noticed how you are taught the basics of, say, uh, some number theory, then errors, um, linear algebra, mostly linear algebra. We also take a look into the methods that work in the background of software such as MATLAB or Mathematica or Maple, even computer-aided engineering software such as ANSYS and Abacus, well-known methods such as finite element method, finite volume methods. What is the mathematics that is driving all of these very powerful techniques and very powerful tools, which is driving engineering innovation? And this course will also try to make you abreast with some of these techniques. Some of you might already be using these software packages in the course of your, say, project work or your daily research, but often we might be using it just as a black box without really knowing as to what is going on behind. And while it is good enough for, say, doing a routine job or solving an assignment, if you want to develop your own model, if you want to develop or create a model which does not already exist, you want to start from scratch, or you are trying to introduce some physics which has not already been very well described, you should know what is going on in the background, and only then will you be able to modify it to suit your needs. You would be able to control aspects, you would be able to say accelerate convergence or take care of stability or say introduce any additional effects which the software package or the existing code does not by default have. And it is for all these reasons that the study of computational methods or computational science becomes very important. Now, as we are well aware, mathematics is the language of physics. When we are trying to model physical phenomena, we must be very fluent and conversant with mathematics. And so, at least for say the beginning of this course, the first few lectures at least, there will be a greater emphasis on mathematical fundamentals. And we will quickly be revisiting some of the more important theorems, axioms, and definitions, which will be useful not just for solving the assignments, which I guess is a priority for some of you, but also to develop a deeper understanding of the methods and to appreciate its nuances. So, with this introduction, let us begin. And the first, at least for today, we'll be recapping vectors and some linear algebra. Now, we know that our, say, classical notion of vectors, which we generally developed in, say, our plus two physics, is that vector is a physical quantity which will have a magnitude, a direction, and sometimes this is missed, but it must also possess a sense. Scalar is again just a quantity with magnitude, it does not have any direction, such as temperature, such as time. Vectors are, say, like force, which has both a magnitude and a direction along which it is acting, velocity, acceleration, and so on. In mathematics, however, a vector is a much more generalized quantity. And while typically our, say, description of vectors is something, say, if I want to describe a force that is acting, it might have in the Cartesian coordinate system, it might have certain components such as, say, y hat plus 3j hat plus 4k hat, for example. And this simply means that this will have certain units, say newtons. What this means is in my Cartesian coordinate system, this is a right-handed Cartesian coordinate system. Along the x direction, I have a force of 2 newtons acting. Along the y direction, 3 newtons, and along the z, 4 newtons. And all of these add together to form one composite force. And all these three are its components, which I can break along these three mutually perpendicular directions. Another way to denote this is with the notation, which simply denotes its three components. Now, it's easy to visualize a vector in 3 dimensions or 2 dimensions. It's very easy to visualize how it is getting broken up into components, how they are adding up, how the triangle law of addition, the parallelogram law of addition of vectors uh, are acting. And yeah, it's very important to remember that just having a magnitude or direction in a sense is not sufficient. Any quantity to be a vector must also satisfy the a parallelogram law of addition of vectors. I'm sure all of you are aware of this. However, this is the case for 3 dimensions. What if we move up to higher dimensions? Say we have a vector in 4 dimensions. Say just 1, 2, 3, 4. Then as we can see, it is something similar to 1 E1 hat plus 2 E2 hat plus 3 E3 hat plus 4 E4 hat, where E1 hat, E2 hat, E3 hat, and E4 hat are the four principal directions or the four mutually perpendicular axes. Later we'll come to see that these are actually the basis vectors. What is a basis vector? Yeah, we'll see in the upcoming slides. Similarly, if we move up to an even higher dimension, say a 5 dimensional or some 7 dimensional, 5, 6, 7, 7 dimensional space, we can still have vectors which will have 7 components. And so, in the very general sense, a vector is simply an ordered n tuple. So in n-dimensional space, a vector will have these n components and it is ordered. So the order really matters. Changing the order will change the sense, the magnitude, perhaps not the magnitude, but it will change the vector. It will result in a different vector. Let us again look at the definition of a vector space. And you will find that during the course of this computational methods, a computational science engineering course, it is very important to be conversant with the definitions and to have those definitions very rigorously understood. Because in the assignments, there may be questions where you are asked to say validate certain hypotheses, or you are asked to find certain relationships or determine quantities which can readily be obtained from some theorem or certain definitions, or it often also happens in examinations or in interviews that you are asked to solve a system of, say, linear equations, and without thinking about it, you just dive in head first, start writing, trying to solve it all around, uh, failing perhaps, and you're not able to solve it for some reason. You think you might have made an error and nothing makes sense, 0 equals 0 sort of a situation, without actually checking at first whether a solution exists or not, whether the system is at all consistent. This course will train you to first check for these conditions before we try to attempt to solve a system, to check whether the solution exists, to check whether you can guess the solution by looking at what conditions the problem presents, or if the coefficients are in a special arrangement which can be simplified very easily. So it's important to be very conversant with all definitions. Let us start with the definition of a vector space. So let V be a set of elements on which two operations called vector addition and scalar multiplication are defined. Under such a situation, the set V will be called a vector space if the following 10 properties are satisfied, and we have 10 axioms, 5 each for the vector operation, vector addition operation, and 5 for the scalar multiplication operation. And satisfying these 10 axioms is necessary and sufficient for any set of elements V to be qualified as a vector space. So for vector addition, if you have two vectors x and y, so in printing, typically they are printed in bold letters, but in writing we may use arrows as we used to use in our plus two physics, or more generally uh, this tilde is used to qualify something or to denote something as a vector. So if x vector and y vector are in V, then x vector plus y vector is in V. That is, the sum of any two vectors must also be contained in the same set as the original vectors themselves. Only then will the set qualify as a vector space. For all x vectors and y vectors in V, x vector plus y vector equals y vector plus x vector. This is called the commutative law of addition. That is, while the vectors themselves are ordered and tuples, and order matters, changing the order changes the vector. While adding up these vectors, it does not matter in which sequence you are going. So this is for the addition of two vectors, even if you have multiple vectors, say three or more, the order does not really matter. So you can have something like, and they will be the same. Of course, while working with numbers and in our algebra, we already know this to be true. But having a rigorous sense of these definitions is important because, as we will see in a few examples during our class, things might not always be so intuitive and so easy to visualize. Say, if you have defined this addition operation x plus y, just like your usual addition with numbers, just adding them up, then things are easy to visualize. But then I can define my addition in some other way. Say, I'll just use a different symbol. See, if I am defining my addition as your typical product, then will the commutative law still hold? It must be checked. And so that is why it's very important to be rigorous with these axioms. They might even appear elementary, except in the cases where you are asked to check and verify whether some uh, set of elements belongs to a vector space, and you see that it does not. And we will see one such example today. For all x vector, y vector, and z vector in V, x plus the sum of y and z vectors should equal the sum of x and y vectors with the z vector, which is the associative law. So even if you are grouping up some terms or some vectors, it should not change the end result. There is a unique vector called the zero vector in V such that zero vector plus x vector equals x vector plus zero vector equals x vector. So I'm just writing it here, x vector plus zero vector equals zero vector plus x vector equals x vector. Now if I'm working with actual numbers, say 5 plus 0 equals 0 plus 5 equals 5, I know that 0 is this additive identity. So even if I add 0, nothing changes, the order, the number remains the same. But that is the number 0. What about this vector 0? Say even if this is a one-dimensional vector, that is, it has only one element, is the element inside necessarily 0? Say if this is a two-dimensional vector, will both its components be zeros and so on? Is this necessarily true? Well, the name zero vector is just a placeholder. It does not mean that the elements inside it are zero. This is just a name, and the zero vector comes from our original sense of having this additive identity, which does not change the number in any way. Just like 1 is the multiplicative identity, you multiply any number by 1, it remains the same. Similarly, 0 is the additive identity, and 0 vector is the additive identity for a vector sense. And we will see that the elements of 0 vector need not be 0, they can be any other general numbers. For each x vector in V, there exists a vector minus x vector such that x plus minus x equals minus x plus x equals 0. And again, we'll see that because this 0 vector need not always contain the numbers 0 as all of its components, the negative x vector can also be sometimes unique. Similarly, we have 5 axioms for scalar multiplication, and I believe these are rather easier to visualize and get a hold of. If k is any scalar and x vector is in V, then k times x vector is also in V. That is a scalar multiple of a vector. In 2 or 3 dimensions, it is very easy to visualize because you have a vector, say something like f vector, then 2f vector is simply twice this along the same direction. And this idea also extends to a more general n-dimensional case. Now, k times x vector plus y vector equals k times x vector plus k times y vector, which is commonly known as the distributive law. Again, k1 plus k2 times x vector. So in the case where you have multiple scalars equals k1 x vector plus k2 x vector. k1 times k2 times x vector equals k1 k2 times x vector, and the number 1 times x vector equals x vector. So some simple things and others somewhat abstract. But solving the example that we'll be looking at shortly will definitely make things clear. We defined V or the vector space to be a set of elements. Since it is a set of elements, it can also have a subset. And since it's a vector space, the corresponding idea would be a vector subspace. Now, it may happen that a subset of vectors W of our original vector space V can also itself be a vector space. And if a subset W of a vector space V is itself a vector space, under the operation of vector addition and scalar multiplication defined on V, then such a subset W will be called a subspace of V. And I would like to mention that most of this material that you see on the slides, they are either borrowed from Professor Ashok Dey's lectures or from this textbook, which is by Dennis Zill. It is on advanced engineering mathematics, and this is among the recommended reading here at IIT Bombay. You might have read other textbooks in your college, but the content will mostly be the same. It's just that the notations might be somewhat different. Now, it is also very important to note that every vector space V will have at least two subspaces. At least V itself, because we know that every set is a subset of itself, and the zero subspace, which contains the zero vector. Now, please note that this is the zero vector, so it is actually this rather than having the number zero. It's a vector. Zero subspace is a subspace since the zero vector must be an element in every vector space, as we just saw. And we have the criteria for a subspace. Any non-empty set W of a vector space V is a subspace of V if and only if W is closed under vector addition and scalar multiplication defined on V. And since it is a vector subspace, satisfies it must satisfy all of these 10 axioms that we just looked at. But often it is sufficient to test just for these two listed here. If x vector and y vector are in W, then there's some x vector plus y vector will also be in W. And if x vector is in W and k is any scalar, then k times x vector should also be in W. The next very important concept is that of linear independence, and we'll look at its definition. A set of vectors x1, x2 till xn vector is said to be linearly independent if the only constants satisfying the equation k1 x1 vector plus k2 x2 vector plus kn xn vector equals 0 are k1 equals k2 equals kn equals 0. That is, the sum k1 x1 plus k2 x2 plus kn xn equals 0 is true only when all of these coefficients are individually 0. K1, K2 till Kn are all 0. If any one of these, even one of these coefficients are non-zero, then the set of vectors will set to linearly dependent. However, this was for the case where you have a countably finite number of elements, x1 till xn, which you can count. What happens if the set of vectors is infinite, countable? So an infinite set of vectors, s equals x1, x2, and so on and so forth, is said to be linearly independent if every finite subset of the set S is linearly independent. And if the set is not linearly independent, then it is linearly dependent. Now we would like to look at the definitions for the basis, the dimension, and span of a vector space. So starting with the basis, consider a set of vectors B equals x1 vector, x2 vector, till xn vectors in a vector space V. If the set B is linearly independent and every vector, so first it is important that B be linearly independent, and if every vector in V can be expressed as a linear combination of these vectors, then B is said to be the basis of V. Let us try to get a physical sense of what is happening here, and maybe a three-dimensional example would help. So, as we were just discussing, in 3D space, say I have this Cartesian coordinate system and I have any general vector R, for instance. Now R is not really in the YZ plane, it is in space because of the paper on which I am writing, it appears to be on the YZ plane. And it will have components on all of these three axes. So say it will have some component on the x-axis, it will have some component on the y-axis and some component on the z-axis. And let these components be Rx, Ry, and Rz. These components are basically projections of the vector on these three axes. Now, we know that in such a case, we can write any such general vector R as equal to Rx times I hat plus Ry times j hat plus Rz times k hat. This we are already very familiar with. But what does it physically mean? I have these three vectors I hat, j hat, and k hat which, by the way, if you would like define, I hat is but 100, j hat is 010, and k hat is 001. These three vectors actually form the basis of the 3D Cartesian coordinate system. Thus, all three-dimensional vectors or all vectors in three-dimensional space can be expressed using these three vectors, and they are the basis vectors. So they might not be unique, there might be other basis vectors also, but the thing to focus on is that B equals I hat, j hat, and k hat is a basis vector for 3D Cartesian space. Similarly, if we extend this idea to an n-dimensional general space, we can see that if we can come up with a set of vectors which will have, say, E1, E2, E3 till En unit vectors, so to say, and if all the vectors in our original set vector space V can be expressed as some linear combination of some or all of these basis vectors, then the set B which contains them becomes the basis vector of the vector space. Similarly, for the dimension of a vector space, it is just the number of vectors in this basis. So for our three-dimensional vector space, the basis vector had I hat, j hat, and k hat, which come up to a total of three basis vectors. So the dimension of our three-dimensional coordinate system or three-dimensional space, 3D space, becomes 3. Similarly, if the basis vector has n such elements, then the dimension of that vector space becomes n. Now, what about the span? If S denotes any set of vectors x1, x2, x3 till xn in a vector space V, then the set of all possible linear combinations of the vectors, such as k1 x1 plus k2 x2 plus k3 x3, so on till kn xn, where you are allowing k1, k2 till kn to take all the values that are possible, and all the ki's are scalars, then this set, which contains all of these linear combinations, is called the span of the vectors and written as span of S. The span of S is again a subspace of the vector, and a set S of vectors x1, x2 till xn in a vector space V is a basis for that vector space if S is linearly independent and is a spanning set for V. The number of vectors in this spanning set S is called the dimension of the space V. So it can get a little heavy and abstract, but then again, uh, what I'll advise is just remember the definitions without trying to always have a physical interpretation. While it is good, but especially in mathematics at this level, it might not always be possible to visualize. Some of you may still be able to visualize these things, but if you're not, do not worry a lot because often you'll be asked to validate hypotheses based on their definitions alone. Now we'll also recapitulate some concepts related to matrices, something that we all are very well familiar with, but then can end up bungling, is the concept of matrix multiplication. So after a stage, I believe all of us started using calculators to do it because doing it with pen and paper is just tedious. But just to remember how it went about, if we have two matrices that we're trying to multiply, first of all, we must check whether multiplication is possible or not. Say if, as the example here says, you have matrix A with m rows and p columns. So this is the notation that I am familiar with, where you denote the dimensions of such a matrix in subscripts. The first dimension or the first notation is generally the number of rows. The second one is the number of columns. And you have a second vector p. Again, its dimension is say p cross n, where p is the number of rows, n is the number of columns. First, we must check whether this multiplication is defined or not. So for matrix multiplication, the multiplication AB is defined if and only if the number of columns of A equals the number of rows of B. So AB, as we saw, is M cross P and B is P cross N. These two numbers are equal, and so this operation is defined. And the sum, the product, say it's some matrix R, will have a dimensions of M cross N. What if we still work with these two given matrices, but the product that we're trying to obtain instead of AB, what if it is BA? Is the operation B into A defined? So as we saw, B has P times, it has the dimensions of P cross N, and A has the dimensions of N cross P. And now when we are looking at the number of columns of B and the number of rows of A, we see that they are not equal. So this operation is not defined mathematically. Note that there is a difference between not defined and not possible, especially in the context of say, some simple concepts such as division by zero. We often say that it's okay, it's definitely it's not infinite, but I have heard people say that it's impossible. Well, it's just that we have not defined it yet. There might be some physical interpretation of division by zero, and in the future we might come up with a way to do it and a standard definition. But right now it is not defined, so we just stop there because we don't really know how to go about it. There is no consensus on what such an operation will give. Similarly, in this case, such a multiplication is not defined. However, in cases where it is defined, that is where the number of columns of A is equal to number of rows of B, we take each of these rows and multiply it with the corresponding, we take each column of B and multiply it with the corresponding row of A. And the operation is illustrated here. Just a quick recap of some important properties related to matrices. All of us are familiar with it. Say if you have matrices A and B and a scalar K, then the transpose of A transpose is A itself. This is the property relating the transpose of a transpose. The transpose of sum of matrices A and B, that is A plus B transpose, equals A transpose plus B transpose. AB transpose equals B transpose A transpose. And for matrices, we know that we can change the order while summing them up. So B transpose plus A transpose is same as A transpose plus B transpose. However, multiplication, the order is important. As we just saw from the example here, changing the order may change the product, and in certain cases, the product need not even be defined. So the transpose of product of AB is equal to B transpose A transpose. When multiplying A with any scalar K, so transpose of K times A equals K times A transpose. That is, multiplication by a scalar does not really affect the result, the transpose in any other way. Another important concept which is often, say, asked in interviews or in examinations is related to the rank of a matrix. And sometimes this idea may not be very clear. The rank of an M cross N matrix A, denoted by rank A or say sometimes just R, is the maximum number of linearly independent row vectors in A. Okay, that's the definition. But in an interview, you might just be given a matrix and you might be asked to find its rank. How do you go about it? There are a few standard ways, and one of them is by something called row reduction. So if a matrix A is row equivalent to a row echelon form B, what a row echelon form is, I believe Professor Day has already uh, defined in his lectures, so it might help if you just revisit his slides. In such a case, where you have a matrix A, which is row equivalent to any row echelon form B, in such a case, the row space of A will equal the row space of B. The non-zero rows of B form a basis for the row space of A, and the rank of A, which we are primarily interested in, equals the number of non-zero rows in B. But how do we go about this row reduction? Typically, there are these three standard operations. One is called row interchange, where you exchange any two rows of a matrix, and typically it might be denoted by a notation such as Rij, where you are interchanging the ith and jth rows with each other. Second is scalar multiplication, and say you had some row. Now you are multiplying it by some scalar. And third is linear combination of rows. That is, you are changing the ith row as some scalar times ith row plus another scalar times the jth row. And we'll be looking at examples of all of these operations, which will help us perceive them more clearly. Again, in your numerical methods courses, you might have come across these elimination methods, which help us solve linear systems. While it is definitely, say, theoretically possible that once you have established a system to have solutions, whether unique or infinitely many, it does not matter, but it does have solutions. It is entirely theoretically possible that you can obtain those solutions manually. But is it the smartest way to go about it? Maybe not. And we'll see how elimination methods make life much easier. And to solve any linear system, we shall use either something called Gaussian elimination or the Gauss-Jordan elimination method. And what are we talking about here? So say typically for a set of system of three linear equations, which will typically be defined as say a11 x1 plus a12 x2 plus a13 x3 equals say b1. For the most general case, a21 x1 plus a22 x2 plus a23 x3 x2 equals b2, and a31 x1 plus a32 x2 plus a33 x3 equals b3. Then we can write this system of linear equations in a matrix form. Ax equals b, or say x equals b, where the A matrix or the coefficient matrix is just A11, A12, A13, A21, A22, A23, A31, A32, A33. The X matrix is X1, X2, X3, and the B matrix is B1, B2, B3. I'm not trying to solve this. As I said, once we establish that a solution exists, we can, go about manually solving it. But it will make life much easier if somehow, based on some operations, which very importantly do not affect the solution of the system, if it could be that, say, some of these elements go to zero, and I would like, say, just one element to survive in the last row, two elements to survive in the second, and all to survive in the first row. What happens now is that in this matrix multiplication, I just have an operation like A33 times X3 equals B3, which gives me, let me just write it out. So it will give me something like, say, 0 x1 plus 0 x2 plus some new or modified A33 prime x3 equals B3 prime. This gives me the value of x3 readily, which is nothing but B3 prime by A33 prime. Now I can back substitute this value in the previous equation, which originally had 0 x1 plus some A22 prime x2 plus some A23 prime x3 equals B2 prime. Now this has become known. This is anyway is going to 0. This is given. A22 prime is also given. Thus I can very easily obtain the value for x2. Of course, as I said, uh, whatever modifications we are making should not affect the solution of the system, or this reduced system that we are coming up with should be equivalent in some way to the original system such that the solutions do not change. This is exactly what we are trying to do with these elimination methods, those being the Gaussian elimination or the Gauss-Jordan elimination. Let us quickly look at what these two methods are. So in Gaussian elimination, we row reduce the augmented matrix of the system until we arrive at a row equivalent augmented matrix in row echelon form. What is the augmented matrix? Typically, it's just denoted by or this augmented matrix, you just add an extra row. So where originally you had A11, A12, A13, you add one additional column which is made up of these elements of the B vector A21, A22, A23, and B2, A31, A32, A33, and B3. This is your augmented matrix. Now, the row equivalent augmented matrix in row echelon form has the following properties. The first non-zero entry in a non-zero row is 1. In consecutive non-zero rows, the first entry 1 in the lower row appears to the right of the one in the higher row, and rows consisting of all zeros are at the bottom of the matrix. If at the beginning they are say in between or on top, we just, as we saw with some basic elementary row operations such as row interchange, we push them to the bottom. This was the Gaussian elimination method. In the Gauss-Jordan elimination method, however, the row operations are further continued until we obtain uh, first an augmented matrix that is in row reduced echelon form, and we'll have the additional property that a column that contains the first entry one has zeros everywhere else. And in the last slide of recap, we'll just see some properties of the inverse and the how to judge a linear system. So in terms of inverses, we know that the inverse of inverse is the matrix itself. So A inverse inverse is A B inverse is B inverse A inverse, A transpose inverse is equal to A inverse transpose. So these might be useful to solve some MCQ type questions in your assignment, where you can use these properties of matrices directly to arrive at the desired solution. Now, this very helpful diagram on the right helps us to classify linear systems based on the solutions. In a case where you have a system such as Ax equal to 0, that is the RHS of all equations is 0, such a system is called homogeneous. And a homogeneous system is always consistent. Again, what is consistent and inconsistent? Professor Day has touched upon in his lectures. So, if for by any chance you have still not watched them, please go and watch. It will be really helpful for strengthening your concepts and for solving the assignments for this week. And since the homogeneous system is always consistent, we know that solutions will exist. It can either be a unique solution or it can be a family of infinitely many solutions. The unique solution x equal to 0 exists when the rank of A is equal to n again being the number of rows, a number of columns of A. So your A is an m cross n ordered matrix. Rank of A is equal to the number of columns. Then you have a unique solution. If for any reason the rank is less than the number of columns, then you will have these n minus r arbitrary parameters in the solution. And depending on what value you choose for these parameters, the family of solutions will keep on changing. Thus, you have infinitely many solutions. Now, this was for the homogeneous case. What happens when the system is non-homogeneous? That is, when the RHS is not necessarily zero. This is called a non-homogeneous system. In such a case, first we must always check whether the system is consistent or not. For consistency, the check is that the rank of the coefficient matrix, that is A, should equal the rank of the augmented matrix A augmented with B. If for any reason the rank of A is less than the rank of the augmented matrix, no solutions exist and the system is inconsistent. Once we have established the consistency of the system, we can check whether the system has a unique solution, which similarly will be the case when the rank of the coefficient matrix equals the number of columns, and we will have infinitely many solutions if the rank of the coefficient matrix is less than a number of columns, in which case you have n minus r arbitrary parameters in the solution. So we have touched upon some of the most important concepts, and after a short break, we will try to solve a few exemplary problems. So let us take a short break here and let us meet in around 10 minutes. Thank you. So, good evening and welcome back. And let us look at a few exemplary problems which will help us solve the assignments for this week. So, in the first question, we are told consider the set V of positive real numbers. I will assume that all of us are aware what real numbers are, and we are looking at just the set of the positive real numbers, so even 0 is included because 0 is neither positive nor negative. If x and y denote positive real numbers, then we write the vectors in V as x vector is equal to x, y vector is equal to y. Now, addition of vectors is defined as x vector plus y vector equals the product of the numbers xy, and scalar multiplication is defined by k times x vector equals x to the power k. Determine whether V is a vector space or not. So now we looked at 10 axioms, and it is sufficient to show that even one axiom is not satisfied to conclude that V is not a vector space. So one by one we will examine all of these axioms. So I'm just reproducing them from the slides. You can refer to them later. The first axiom is that if x and y vectors are in V, then x vector plus y vector is also in V. Now, for this case, where the set V contains all the positive real numbers, x vector is equal to x, which is greater than 0, and also y vector is equal to y, which is again greater than 0. The sum x vector plus y vector is defined as the product of x and y. Since x and y are individually greater than 0, the product is also greater than 0. Thus, it also lies in the set V because it is a set of all positive real numbers. So, the sum x vector plus y vector equals xy lies in V for all x vector and y vector that lie in V. So, the first axiom is satisfied. The second axiom for all x vector and y vector in V, x vector plus y vector equals y vector plus x vector. Now, since we know that x and y are greater than 0, x vector plus y vector is defined as xy. Y vector plus x vector is defined as yx, which we know to be equal to each other. So this is also satisfied. Let us look at the third axiom for all x vector, y vector, and z vector in V. X vector plus y plus z vector is equal to x vector plus y vector plus z vector. Let us try to expand these. So x vector plus y vector plus z vector will actually become xy plus z vector, which will become xyz. X vector plus y plus z vectors will become x vector plus yz, which again becomes xyz. So third axiom also stands satisfied. The fourth axiom of vector addition mentioned that there exists a unique vector zero vector in V such that zero vector plus x vector equals x vector plus zero vectors equals x vector. Now, we had briefly touched upon the idea that these zero vector may not contain elements which are all zero. Let us say if we assume that what happens, let us say it can also be zero, it need not necessarily be so. But what if the zero vectors contains zero? So in this case, zero vector plus x vector, depending on the way that we have defined it, becomes 0 times x, which becomes 0. Whereas it should have been the x vector itself. So clearly, the set of 0 to be the element in the 0 vector does not satisfy the requirements of a vector space. Then can we cleverly choose another such 0 vector which can help us satisfy the requirements for a vector space? Yes, we can. Let the 0 vector contain the element 1. Then 0 vector plus x vector shall equal 1 times x, which shall equal x, which is equal to the x vector, and thus our 0 vector in this case has just the element 1. And by the way, we ended up satisfying the fourth axiom as well. Let us look at the fifth axiom. For each x vector in V, there exists a vector minus x such that x vector plus minus x vector equals minus x vector plus x vector equals 0 vector. Again, remember, we are talking about the 0 vector and not 0. Now, say typically when we are dealing with just numbers, if I need to find an additive inverse, I would just have gone with the negative of the same number. Say if x is 5, then minus x would have become minus 5, and 5 minus 5 shall equal 0. But here, our 0 vector is actually the number 1. And so, if we choose our negative x vector to be equal to simply the negative of the number x, and what we end up with is as follows. Remember, we have defined the sum operation as the product of the numbers. Then this will become x times minus x is equal to minus x square, but our 0 vector is equal to 1. These are not matching. Then what is the proper choice of this negative x vector? If we cleverly choose the negative x vector to be equal to 1 by x, then we see that x vector plus negative x vector equals x times 1 by x equals 1, which, if we remember, is our 0 vector, and we end up satisfying the fifth axiom as well. Thus we see that the choice of the additive inverse or the 0 vector and so on need not be analogous to those that we typically choose when working with numbers. This can be very different, and thus it is very important to be conversant with the definitions that we looked at. The scalar multiplication axioms are rather easier to satisfy, and we'll just go over them quickly. So, say the sixth axiom for any scalar k, if x bar is in V, then k times x bar is also in V. In this case, we have defined scalar multiplication as x times k, and since k is greater than 0, x times k will also be greater than 0, and that is also in V. Thus, this axiom is satisfied. The seventh axiom being that k times x vector plus y vector equals kx vector plus ky vector. And let us work through this. So k times x vector plus y vector equals k times xy equals xy power k, kx vector plus ky vector equals x power 2. Just a second. It will be easier if you just continue working with this only. So x power k times y power k and x power k, as we know, is equal to kx, and this is equal to ky, and since x and y are multiplied, this is but kx bar plus ky bar. So this axiom is also satisfied. The eighth axiom, k1 plus k2 x bar is equal to k1 x bar plus k2 x bar. And let us examine it. k1 plus k2 x bar is equal to x power k1 plus k2, which becomes x power k1 times x power k2, which becomes x k1 plus x k2 based on how we have defined additional multiplication, scalar multiplication, and this will turn out to be k1 x vector plus k2 x vector. Hence, this axiom is also satisfied. The ninth axiom, k1 times k2 times x vector equals k1 k2 times x vector. And let us work through it again. So k1 times k2 x vector equals k1 times x power k2 x power k2 power k1 equals x times k2 k1 equal k1 k2 times x vector, and hence this is also satisfied. For the last axiom, 1 times x vector equals x vector, and just to remember that we have defined k times x vector equals x power k. 1 times x vector is equal to x power equals x, which is nothing but the x vector itself. So we see that all 10 actions are satisfied, and since all the actions are satisfied, we conclude that V is indeed a vector space. Let us look at the second question and to check whether the given vectors are linearly independent or linearly dependent. So the first one, since all of these vectors have only two components, we can do this by some simple inspection or even just plain guesswork. So the first vector is 1 1, second is 0 1, and the third one is 2 5. And remember, what we are trying to do is, if we can somehow come up with a linear combination of them which adds up to 0 without all of the coefficients being individually 0, we can say that they are linearly dependent. So if I just multiply this with 2, because I'm seeing that the first element here is 1 and here it is 2, and multiply this with minus 1, then at least the top row goes to 0. For the second row, we have 2 minus 5 is minus 3 plus 3, and this will indeed come up to be 0. And since I have found one set of coefficients k1, k2, k3, which in this case are 2, 3, and minus 1, which bring the linear combination sum of linear combination the linear combination to be a 0, then the set of vectors is clearly linearly dependent. And this is not even the only set of coefficients which may bring you to this conclusion. There can be others, and you are free to come up with your own solution. It's not unique. For the second case, however, We might still be able to do it manually or via inspection, but it'll be more systematic if we do it via row reduction. And whenever you are given three vectors to check for linear independence, the first step is to put the vectors as the rows of a matrix, say A. And as we just saw, if the rank of A is equal to the number of vectors that we put, which in this case is 3 by the way, then the system is linearly independent. Otherwise, it is dependent. So the three vectors are 1, 2, 3, 1, 0, 1, and 1, minus 1, 5. And we have put them as the rows of a matrix. Now, in a typical elimination fashion, first we will try to make these first column elements 0 using the first row, and so the second row will be transformed as R2 minus R1, the third row also, and what we'll end up with is 1, 2, 3. 1 minus 1 is 0, 0 minus 2 is minus 2, 1 minus 3 is minus 2, 1 minus 1 is 0, minus 1 minus 2 is minus 3, 5 minus 3 is 2. Now we'll try to make this element 0, and the way to do it is R3 goes to R3 minus 3 by 2 R2. First row remains unchanged 1, 2, 3, second also 0 minus 2 of 0 minus 3 by 2. This becomes 0, 2 minus 2 plus 3, this becomes 5. And while we can stop here, just for consistency, what we'll do is have an additional step where we have these repeating coefficients, and we'll just do a scalar multiplication to bring them to 1. So the second row is transformed as minus half R2, and the third row is transformed as 1/5 R3, and then this becomes 1, 2, 3, 0, 1, 1, 0, 0, 1. And this is the row echelon form. And we see that in the row echelon form, there are 3 non-zero rows. But this is the exact definition of the rank. So the rank of A is equal to 3, which, by the way, is equal to the number of vectors. And as we just saw, if the rank of the matrix equals to the number of vectors, then the system is linearly independent. Some MCQ type questions. A given matrix B is subjected to right-hand multiplication of a permutation matrix. What changes can be observed? Now, just to give you a hint, Professor Day illustrated pre-multiplication or left-hand multiplication in one of his lectures, which goes something like multiplying any given matrix with the identity matrix changes the rows. And so it can be seen that post multiplication or right hand multiplication of permutation matrix will bring about a change in the columns. But please verify this fact. Sorry. Question 5, again a multiple choice type question. Oh no, it's not a multiple choice. So you have a given matrix A, which is a 4 cross 3 matrix, and B, which is a 4 cross 4 matrix. What would be the dimensions of the resultant matrix when you have the multiplication operation AB? So this is something similar to what we did. A is 4 cross 3, B is 4 cross 4. When we are trying to multiply AB, we check the number of columns of A, compare it with the number of rows of B, and see that they are not equal. So this operation is not defined. When we are trying to perform the operation BA, number of columns of B is equal to the number of rows of A, so it is defined, and the product will have dimensions of 4 cross 4. Sorry, 4 cross 3. Suppose A is a 4 cross 3 matrix with only one vector as the basis for its null space. Determine the rank of A. So at first this question might appear somewhat difficult because we're not really given a lot of information, but we must remember uh, something called the rank nullity theorem that was discussed by Professor Day in his lectures. And just to briefly recall, the rank nullity theorem for any matrix A of dimensions m cross n states that the rank of A plus the nullity of A equals the number of columns of A. And with our notations, R plus S equals N. In this case, we are given that M is equal to 4, N is equal to 3. These are the dimensions of A. The nullity S is equal to 1, as there is only one vector which forms the basis of the null space. We are required to find the rank. If we put it into our equation, R plus S equals N, R plus 1 is equal to 3, R is equal to 2. Thus, the rank of matrix A is 2. The next question. Suppose A is an m cross n square matrix with rank R which is less than n. Then, for the consistent system Ax equals to B, what is the number of solutions? This can be quickly answered by referring to a chart. We are already told that the system is consistent and the rank is less than the number of columns. So if we refer our helpful flow diagram, we are already told to assume that the system is consistent. And it does not matter whether it is homogeneous or non-homogeneous, because in both cases we use the same criteria. Since the rank R is less than n, which is this case right here, there will be infinitely many solutions. Let us check what are the given options. only one zero insufficient data? No, we can clearly surmise that there will be infinitely many solutions. Okay, there is one question on Gaussian elimination, Gauss-Jordan elimination, but we'll not touch on it today due to paucity of time. We'll be discussing it in the next class along with any doubts which you might have from today. So thank you. That is all for this session. I would like to thank you for tuning in to this live session for the course on computational science and engineering. I am Sourav Goswami from IIT Bombay. Thank you.